Hello and welcome back. In example 3, we're looking at the integral of secant to the fourth x times tangent to the third x dx. And before we tackle this example, let's recall what the derivatives of secant and tangent are. If you ever forget them, there's a story that goes along with this. So suppose you forget what the derivative of secant x is, and you're in the middle of a test, and you turn to your friend and you go, "Psst, what's the derivative of secant?" And your friend looks at you and says, "Dude, you just told yourself the answer." What does he mean by that? Well, if you write out psst, like this, PSST, and you ignore the P, P is usually silent anyway, and you just focus on the SST, you can write for the S, secant, and then for the other S, secant, and then for the T, tangent. And this gives you a way of remembering the derivatives, because the derivative of secant is secant times tangent. So the derivative of secant is secant times tangent. Just reading from left to right. Derivative of secant is secant x times tangent x. And then the derivative of tangent, going from right to left, derivative of tangent is secant times secant, which is secant squared. So the derivative of tangent is secant x times secant x, which is secant squared x. Great. As long as we're talking about this, it's probably worth it to remember the derivatives of cosecant and cotangent. So let's continue this on. We're going to write the same exact thing, but instead of secants, we're going to write cosecants. Instead of tangent, we're going to write cotangent. So let's do this. Cosecant, cosecant, cotangent. And we'll put a little negative in front, which will handle the negative signs that come out of taking the derivatives of the C trig functions, right? Derivative of cosine, cosecant, and cotangent, they're all negative derivatives. So any derivative of a trig function that starts with a C is going to be a negative result. It's just a mnemonic to help you remember. There's not like a mathematical reason for that. I mean, after all, we just made up these names to represent these ideas. So if we put that negative in front of the cosecant in the middle, everything will work itself out. The derivative of cosecant is negative cosecant cotangent. Derivative of cosecant is negative cosecant cotangent. And the derivative of cotangent is negative cosecant times cosecant, which is cosecant squared x. There's a little reminder of the derivatives of secant, tangent, cosecant, and cotangent. Now we want to keep these in mind when we're trying to solve one of these integrals here. So we'll see how that works out. In our example, we have an even power of secant and an odd power of tangent. Now, one of our goals is going to be to save part of this integral to be with the dx. We want to have the derivative of either secant or tangent to be with the dx, because again, we're going to use this technique of substitution for this integral. Or we're going to try to, at least. Now, if we save, so we either want to save a secant squared x or a secant x tangent x. Let's try saving a secant squared x off to the side and see where that gets us. We'll try saving a secant squared. If we do that, we're going to have two secants left. So we'll have a secant squared left. And the tangent cubed will still be there. So we've saved a secant squared x to be with the dx. Again, our goal is substitution. So eventually we want to have whatever's left here, we want to let u equal tangent x, so the du will be secant squared x dx. Okay, so our goal is to make sure that everything here left over is in terms of tangent. And that's great because secant squared x, that's got an even power of secant. And we can use that Pythagorean identity to help us out. Actually, let's take a moment to review that table of those trig formulas. Remember that you had the relationship between sine squared and cosine squared is sine squared plus cosine squared equals 1. Remember that you can take this same identity and convert it to get relationships between tangent and secant, and then cotangent and cosecant. All you have to do is take sine squared plus cosine squared over 1, or equals 1, and divide it by cosine squared x, and you'll get tangent squared x plus 1 equals secant squared x. And that's because sine squared x divided by cosine squared x equals tangent squared x, and cosine squared x divided by cosine squared x equals 1, and then 1 over cosine squared x is secant squared x. You can also use this identity to get the other one. All you have to do is divide by sine squared x. Oops, hit the scroll bar accidentally. That's supposed to be an x there. So divide by sine squared x, and you'll get 1 plus cotangent squared x equals cosecant squared x. Okay, so knowing these, we can convert any even power of secant into tangents, and we can convert even powers of tangents into secants. Similar for cosecants and cotangents. So let's see where that helps us out in example 3. Example 3, we want to convert these secant squares into tangents, and that's perfect. Secant squared x is going to be equal to tangent squared x plus 1. We'll write that off to the side just to remember what we're doing. So secant squared x equals tangent squared x plus 1. We have tan squared x plus 1. The tan cubed x we'll leave alone, and then we've got secant squared x dx left over. So let's see where we are in our strategy. It's kind of like a chess problem. You have to look, a couple steps ahead, and then you'll be in a really good position to checkmate the problem. So here we have most of it is tangent x, and then over here with the dx we've got secant squared x. So now it's perfect. If we let u equal tangent x, the derivative of u, the du, is right there. It's secant squared x dx. So this is perfectly set up for substitution. It's like a perfect pitch. And we're just going to smack that ball and get a home run. All right, so substituting, we have integral of u squared plus 1 times u cubed, and then du. Then we'll distribute the u to the third. Integrate term by term, so we get u to the 6 over 6 plus u to the 4th over 4 plus c. And then just make sure you go back to x. Now we had let u equal tangent x, so replace the u's with tangent x. So we get tangent to the 6x over 6 plus tangent to the 4th x over 4 plus c. Great. Now you might be asking, would it work if we saved a secant x tangent x? And the answer is yes, it could work out. And I'll leave that to you to give it a try. Your answer will look a little different. It'll be in terms of secant. But if you use a bunch of trig identities, you can eventually get from this answer here to the answer that you would get if you used a substitution with secant x. Just dropped my stylus. There it is. All right, so that's example 3. Thank you so much for watching, and see you in the next part.